So in principle, we are integrating from 0 to a. On the other side, assuming also that you have let's say the screenshot of the previous class, that here you would have C1 integrating from 0 to a sine 2, let's do first, sine pi y over a sine 2 pi y over a dy plus the coefficient C2 integral 0 to a sine 2 pi y over a sine 2 pi y over a dy. We continue again, plus C3 integral is the same thing. Here we have sine 3 pi y over a sine 2 pi y over a. Maybe the best would be if we use color-coded. Wait a second, because this might make 2 pi y over a. Sine 2 pi y over a. Now, dy. Meanwhile, we also know that sine 2 pi y, sorry, not 2 pi, this is m times sine n pi y over a, this is m, integrating from 0 to a. It is either 0 or a over 2. It is 0 where m is different from n. It is a over 2 where m is equal to n. Now, what do we have here? Let's have a look at this multiplication. This is coming when n is equal to 1 and m is equal to 2. This other term, this corresponds to n equal to 2 and m equal to 2. Here, this is n equal to 3, m is equal to 2. So it looks like we keep m is equal to 2 because we want to determine this value, okay? And based on this property, we can simply say, so we can continue again like this, right? We can multiply, we can change the n again and again, but we know that whenever m is different from n, this would be 0, okay? This is also 0. So here we have, this is always equal to 0, plus, this is C2, this constant C2, times a over 2. So the only integral which is different from 0 is a single one, which corresponds to coefficient C2. So then it is obvious that we'll keep adding some more zeros, which is useless in fact. But it looks like once we multiply by this term and we integrate from 0 to a, this whole thing is equal to this value. Now, then what remains for us is just we calculate this integral and then we substitute for C2. So this is why the orthogonal functions are useful. So sine and sine, they are harmonic functions, they are orthogonal. That's why they are easy to work with whenever we want to determine these types of coefficients. Now that we see this example, this is why it is very important or excessively useful to have polynomials which are orthogonal, as we wrote in the previous session, where legendary polynomials of order n times a legendary polynomial of order n, integrating from -1 to 1. This would be 0 if m is different from n, and it is different from 0, let me call it some value k, if m is equal to n, okay? So the similar aspect we used here for sine to sine, we can use it also in here. So for a moment, so it looks like C2, it was equal to 2 over a, okay, because 2 over a times the integral from 0 to a b 0y times sine 2 pi y over A dy. Okay. Now this is the for C2. The general expression, it can be written like this. It's also easy to generalize this one. This would be 2 over A integrating 0 to A, whatever the initial condition V0y is, times sine of n pi y over A dy. So what we see here is that it looks like now we have a complete solution, because now we can also determine what is this coefficient C here. One possible example is the following. Let's assume that, so let's try to remember also what was our definition of the problem. We had a plate here, right? And we had also another conductive plate on the top, where this was grounded. The lower plate is also grounded. Let's assume for a moment that we are going to add another plate here, but let's keep this at a constant voltage. Let it be independent of Y. So let's assume that you connect it to a battery, which is 3 volts. And then this value would be, let's call it 2 volts, okay? Or let's write it V0. Then the Cn would be equal to 2V0 divided by A, where A, it was a distance between the 2 plates, integrating sine n pi y over A. Now, this integral of n sine sine n pi y over A, integrating with dy. So let's write dy like this. But it's good. So let's multiply inside this differential by n pi. If we multiply with n pi here, we have to divide also here by n pi. Okay. So this is dy. We multiply by n pi. We divide by n pi. So we have changed nothing so far, because you know that the differential of d over 2x is equal to 2 times dx, right? So this moves in and out. Then what is left here? We have to divide here by a. This is a constant. We divide here by a, but that means that we have to multiply here by a. So you see, so far we changed nothing, only that we can now integrate this expression. The integral of this expression, integral of sine, it is equal to minus cosine, and this is from 0 to a. So, and these two a's cancel out each other. This would be equal to 2v0 divided by n pi. As we said, integral, it's equal to minus cosine of n pi y over a. The limits of the integral, they are from 0 to a. Similarly, I'm moving upward. This is 2v0 divided by n pi. We can write this one as cosine n pi y over a. We remove the negative sign by changing the limits. So this is from a to 0. Then this would be equal to 2v0 divided by n pi multiplied by, we substitute the 0. Cosine 0, it is 1. Minus, if we substitute here a, this becomes minus cosine a over a. This is cosine n pi. Okay. So it looks like the coefficients that we have to include, they can be written. Let me see what is the best place to write this down. Let me write this one here, because this was just orthogonality relationships, which they are always true. But let's write here that apparently Cn, it is equal to 2v0 divided by n pi 1 minus cosine n pi. Okay. So let's have a look at what does this function look like? Now, we want to see how does the cosine function, how can we represent it? A cosine function, it is the projection of the harmonics onto the horizontal axis or onto the x-axis. So cosine n pi, the values that we are going to obtain is that for n1, this is cosine pi. What is cosine pi? It's -1, okay? So these values will be -1 when n is 1. This is here. When n is equal to 2, we get 1 when n is equal to 2. Then when n is 3, cosine 3 pi is -1 again when n is equal to 3. So it looks like it is -1 when it is odd and 1 when it is even, which means that Cn, so let's say if it is odd, we get 1, -1, we get 2. So this is equal to 4v0 divided by n pi when n is odd value, okay? So this is Cn, but at the same time, Cn is equal to 0 because when n is even. Okay. Then, based on this information, we can finally say that the how can we? Well, we can write this one in several different ways, but here. Now, I hope this part is clear. We're just trying to show how most of the terms, they cancel out. It's good for you if you work this one out at least once in your notebooks. But finally, the potential as a function of x and y, this would be equal to the, so this was Cn e to the power minus n pi over a x sine n pi over a y. Then we generalized, not we generalized, we assume that if v0y is equal to a constant value v0, that means that this integral, it would be a relatively simple expression. So this v0 will get out, and then in that case, the potential as a function of x and y would be equal to Cn, this would be equal to 4v0, and 4v0, it is constant. Divided by pi, it is also a constant. So we can write here 4v0 divided by pi, summation over n of 1 over n times e to the power minus n pi over a x sine n pi over a y. But this is true only for n odd numbers, when n is equal to 1, 3, 5, 7, and so on. And the rest, they are all equal to 0. So apparently, this is the, let's say, the complete solution of this problem that we are working. Now, we can make this problem slightly more difficult, which, for example, we can assume, so here, we just made an assumption where we said that this b0y, it was a constant value, and we got it out of the integral. We can try another value. Let's erase this one, just to see how the solutions could play out. Let's assume that the potential at the barrier, where for x equal to 0, this can be equal to y, okay? So it could be a value which, if it is equal to y, it can be a value which starts from 0 to a, okay? So if a is 1 meter, that means that the potential is going to change from 0 to 1 volt along the y-axis. And then we would have to take this integral, which would be, this is y sine n pi y over a dy. So in this case, we would have to to modify a little bit these values. So instead of y, we would write, so this is the integral, we would write n by y over a, okay? And here we have to divide n pi over a, okay? So far we have changed nothing. This is still y, only that we have taken this constant out. Then we have sine n pi y over a dy. Now we can take this square, and instead of here we write n pi y over a. So this integral, it comes up like this. At this stage, we can do a change of variables, and let's not forget this is from 0 to a. Now we can denote a new variable, so we can write this one. This is equal to a over n pi whole squared. This is u, or let's write this one. Let's say theta sine theta d theta. Okay, so let's assume this is the case. Now, how can we integrate this case? This is the type of integral where integral of u dv is equal to ub minus b du. So here we can denote u, which is equal to sine theta d theta, du. This is equal to, what is the derivative? This is cosine theta. And wait a second. No, this is wrong. Maybe we should do it like this. So du cosine theta d theta, and dv. Wait a second. No, it's better. This would be a better change. I'm sure the class is full of students who can do this faster than me. How to integrate this using this property, the integral of u dv. It's equal to uv minus b du. So that's what we're trying to implement here. I'm just having a hard time to write this down. So du is sine theta d theta. This means that u is equal to minus cosine theta. So we integrate both sides of the equation. Then what is left? This one we substituted. What is it to u dv? I'm seriously having, so dv, of course, you notice this one before me, and you say, Professor is still doing this wrong. So dv, it's equal to sine theta dv, d theta. Then the u is equal to theta. U is equal to theta, then du is equal to d theta. We're having a better time here, so then let's continue integrating here. This will be equal to uv, which uv is right here and here. And this is equal, and let's not forget the integral, it is from y equal to 0 to y equal to a. Okay? And this is uv minus, let's do it like this, minus theta cosine theta, minus the integral of b du, minus the integral of v du. The v is this, du is d theta, minus, this is plus cosine theta d theta. This integral, this is equal to sine theta, okay? And sine theta, and we can substitute now what was theta. This was the result from the previous example. Let's take this out. This becomes like a marathon. We can do this faster. And this is equal to a over n pi whole squared. And then multiply the whole term, which is theta times cosine theta. But this is with a minus sign, and this is from 0 to a. We can take the minus sign away, and we can make this from a to 0. Okay. But then, instead of theta, we can write here n pi y over a times cosine n pi y over a plus sine of n pi y over a, and let's not forget the limits here will be from a to 0, sorry, from A to 0, but the limits here will be from 0 to A for reasons that you know better than me. So here this is A divided by n pi all square. Then if we substitute here n equal to 0, this whole term gets 0. Then this is 0 minus, if we substitute here A, this is n pi, because A is cancelled out, times cosine of n pi. Okay. Cosine of n pi. Plus sine n pi, so this is really some good piece of work. Sine n pi minus 0. Okay. Now I can leave this to you to have a look. Oh, this is really an interesting problem, because for any n, it looks like. Oh, let's try to monitor this carefully. So this is equal to a over n pi all squared times n pi. Now let's notice what happens when n is odd. xy. So let's assume n is 1. When n is 1, here, or odd, it would be cosine. And by the way, wait a second, this is n. In fact, this sign, this will always be equal to 0, right? Because it's sine pi n. And sine pi n is an integer number. It's going to be pi, 2 pi, 3 pi, 4 pi, 6 pi, and so on. But it will always be equal to 0. So this terms, it cancels out. Only that we're going to have n pi times or minus n pi when n is odd, or plus n pi when n is even. Okay, this is interesting. So we found the integrand, which is shown over there. Now, it could be a good exercise for you if you work out the final results. So this was the integrand of y. Yeah. Let's not forget that this was Cn, this was C2, this was Cn. Well, all we did is that we substituted in this expression, we went a way up. We substituted v0y as y. This became here, this here, this here. We moved ahead. And by the way, we can even cancel a couple of terms. I really like when you get a difficult problem, but everything plays out being much simpler. So in this case, we find that Cn is equal to a squared over, so it is actually we have minus 1. So this is equal to, so how can we write minus 1 to the power n? Yes, when it is odd, so this is minus 1 to the power n, which means that when n is odd, this will be minus 1. When n is even, this will be plus 1. So this is good this way. Minus 1 is now generalized, minus 1 to the power n times a squared over n pi. Okay, that is good. Okay, so we found the Cn, and let's not forget, this Cn, it was, for this case, when v0y, it was equal to y, okay. And this Cn, it was when v0y, it was a constant, v0. So we can see the nature of how these parameters play around or how they change as a function of the all of these values. So again, in this expression, if v0 is equal, the potential is equal to v0, we substitute this expression here. If v0y is equal to y, we substitute this expression here. And to help the visualization, if this is X and Y, this means that if A, which was the top part, so this plate was grounded, this bottom plate is also grounded. If this is equal to 5 meters, this means that the solution that we just found, it considers a situation where the potential at the bottom it is 0. You get higher, it gets 1 volt, higher 2 volt, 3, 4, up to 5 volt. If we have a potential which gradually increases this way, the general solution, it will have these elegant terms substituted for Cn times the rest. Okay. Any question? Okay. Now, another important aspect that we could discuss right now is the issue of finding the potential and the electric fields in configurations where a charge distribution is in proximity of a conductive system or a conductive layer. In this case, So imagine for this kind of problems, they are often even shown in science fairs, or very good students in high schools, they might have posed this type of problem, which might include a cloud which has a huge charge, and this is over the Earth, over the planet Earth. Now, Earth, it is a conductor, or it is easily, you can easily move free charges onto the Earth, and what happens is that the effective reconsideration of the problem is of this nature. So if you have a charge Q and we need to determine the potential at some point P, this is easy. But the moment that we, if this one is close to some conductive layer, so this is conductive material, conductive. Instead, close to the conductive layer, what happens is that because of this Q and this Q, it has field lines that go like this and also like this. And because this is what they do, okay, here, and of course it goes also everywhere. And these field lines are going to attract negative charges at this layer. In the end, having this charge Q here, it is effectively the same as producing at the other side another charge with the same magnitude. So in this case, then in order to find the potential at some point P, it would be equivalent to, so if we did not have the conductive layers, it would be easy. We'll just find this distance, and this would be equal to K Q over R, okay, that's it. But now we have the conductive layer, the problem now, it is equivalent to having plus Q and another charge with the same magnitude minus Q. And now, if you want to find the potential at point P, we have to consider the contribution from here and the contribution from here. And then the potential would be equal to K Q over R plus K minus Q divided by R minus. R plus, we are denoting the distance of the positive charge to point P. R minus, we denote the distance from the negative charge to the point P. And in order to do this, in fact, we can leave. So this is the general approach, and we can solve at least one. Let's see. So let's assume that the distance from the conductive layer is d, and this is also d, and this expression, it can be written again as kq 1 over r plus minus 1 over r minus, and then the point P, it is assumed to be at location. What's wrong with this? So let's point P. It is located at this specific place, or x, y, z. Then here we consider that x-axis here, or let's see which one is the best way to use. Yes, this is x-axis, y-axis, and z-axis. So then this specific distance, it can be written as, so this would be equal to kq 1 over. Now this is just the magnitude of this vector, which in fact it will be the Euclidean distance between 2 points. One point, it is 0, d and 0. Okay, so this is the x coordinate, this is the y coordinate, this is the z coordinate, minus another point, which is x, y, z. The Euclidean distance between these 2 points, it is simply 0 minus x all squared plus d minus y all squared plus 0 minus z all squared square root. Okay, so this would be the specific distance. Then we have the other point. So this was the plus q, and this is plus q. The other charge, the negative q, we have the Euclidean distance from this point to here. How can we determine it? This is the location of this one. It is located at 0 minus d 0. So this is 1 point minus the general expression of x, y, and z. And the distance between these two, it is 0 minus x all squared plus minus d minus y all squared plus 0 minus z all squared square root. So this is what we get in the end. Now, this x squared, we know that a minus b squared, it is equal to b minus a squared. And we can also rewrite this one as x squared plus y minus b squared plus z squared minus x squared plus y plus d squared plus z squared. So this would be the potential at any point x, y, z as a result of a charge q located in the proximity of a conductive layer or a conductive structure. Okay. Do you have any question?